pleasant day to you all children. I hope you all are doing well in this pandemic. Yes, children, today in this session I am going to talk about something you have seen throughout the course of your life. Yes, something you have seen a lot but you know very little about it, and something that separates day from the night, and it comes with many colors but collectively it is white. Okay children, can you guess what is it? I'll give you some more clues. When we talk about its speed, nothing can be compared to the power of its flight. Believe me or not, this is responsible for your sight. Can you guess what it is? Yes, that is light. Today our topic is light. Let's learn about light. So in this lesson, what are the parts we are going to highlight? See children, learning objectives. First, we are going to focus on the properties of light. What are the two main properties of the light? Yeah, reflection and refraction of the light. Reflection we have seen in our lower classes. Today's main topic is refraction, and also we are going to see the laws. Next children, the scattering of the light and various kind we are going to focus on. Okay, let's start with the properties of light. What's the first property of the light? You know pretty well that the light is in the form of energy. Yes, that we know pretty well. Next, light always travel along straight line. Light travels along straight line. This rectilinear propagation of the light we have studied in our lower classes, and we have seen the pinhole camera also, isn't it children? Yes. Next one is light does not need any material medium for its propagation. Yes, it can even travel through vacuum. This also we know very good. Next, the speed of the light in vacuum or air, it is how much do you know? 3 into 10 to the power 8 meters per second. That means 300 million meter it can travel in 1 second. Yeah. Next one is, actually children, the light has a dual nature, that is particle nature and wave nature. Here when it is in the form of waves, it is characterized with two parameters, that is wavelength and frequency. So they are related in the equation C equal to nu into lambda. That is, the velocity of the light is the product of the frequency and the wavelength. The next property is different colored light has a different wavelength and different frequency. Clear? And the next one, among the visible light, the violet has the lowest wavelength and red has the highest wavelength. Clear? Keep this in your mind. I will be telling this afterwards. The next, last but not the least, when the light incident on the interface between two media, it is partly reflected and partly refracted. We just ignore the reflection. Let's talk about the refraction. That is the highlight of our class. Yes. Now our topic is the refraction of the light. The water and the pencil. I have kept one full pencil, but can you see the pencil is broken here? Yes. Yes. Let us see why it happens. Next, see the water and this arrow mark. This arrow mark is pointing towards this direction, but when we see it towards the water, can you see it is moving in the opposite direction? Yeah. Can you tell me what is the reason for these two? Yes, that is because of the bending of rays. This bending is due to the refraction of light. Let's see what is refraction. When a ray of light travels from one transparent medium into another obliquely, the path of the light undergoes deviation. This deviation of the light ray is called the refraction. Let's explain. What do you mean by the transparent medium? When it travels from one material to another material. Clear? Medium means some material. Obliquely means incident at an angle. Clear? And the path of the light undergoes deviation means it changes its direction. Therefore, here the ray of light travels from one medium to another transparent medium. What happens? When it incident at an angle, it changes its direction. This change of direction is known as the refraction. Why it is happening, children? Just because the difference in the velocity of the light in different medium. That is the main reason. Okay, let me explain clearly. Consider this is the air medium, this is the water medium. Clear? Now this is the line which divides these two medium. Okay, here the ray which falls on this interface, that is known as the incident ray. So what happens here? At the point of interface, what happens? Instead of it taking the straight line path, it changes its direction. Okay, so the change direction, this ray is known as the refracted ray. Fine. Now see the perpendicular dotted line, this we call it as a normal. Okay, fine. This is the incident ray, this is the normal, this is the refracted ray, and the angle between the incident ray and the normal is known as the angle of incidence, and the angle between the refracted ray and the normal is known as the angle of refraction. Okay, children, let's explain the laws of refraction. See here, the first law is the incident ray, the refracted ray of light and the normal to the refracting surface all lies in the same plane. Everything lies in the same plane. Just now we have seen, isn't it? Incident ray, normal, refracted ray, everything lies in the same plane. Okay, fine. Second law of refraction is the ratio of the sine of the angle of incidence. You know what is angle of incidence? Yes, that is the angle between the incident ray and the normal. Clear? As well as the angle of refraction is the angle between the refracted ray and the normal. Yes, the ratio of the sine of the angle of incidence and the sine of the angle of refraction is equal to the ratio of the refractive indices of two media. We have taken two media, isn't it? Air media and water media. So it is equal to the ratio of the refractive indices of two media. This is otherwise called as a Snell's law. Now let's focus on what is refractive index. Clear? The refractive index is here the ratio of the speed of the light in vacuum to the speed of the light in the medium. So this ratio is known as the refractive index. It is denoted by the letter mu. Clear? Therefore, this refractive index only gives us the clear idea of how fast or how slow the light travels in the medium. Therefore, the speed of the light in the medium is slow if the refractive index of the medium is high and vice versa. Now we have cleared that what is refractive index. Clear, children? Okay. The next one is types of sources of light. Actually, we have two types of sources of light. First one is the monochromatic source of light. Another one is a polychromatic source of light. Let's focus on monochromatic source of light. It is if the source of light produces, mono means only one, single. If it produces a light of single color, then it is known as a monochromatic source of light. Yes. So, the best example for this is a sodium vapor lamp. It produces only the yellow color, you can see to it. Clear, children? The next one is another type of source, a polychromatic source or composite source of light. If a source of poly means what? Many. If it produces different colors, then it is known as a composite source of light or polychromatic source of light, and the best example for that is sun, because it has many colors with it. Okay, children? And also another one example, mercury vapor lamp. Have you seen the mercury vapor lamp here? Yes. See, children, how it produces the many colors. See, mercury vapor lamp. See how it produces band of colors, isn't it? This band of color is known as otherwise called as spectrum. Clear? It's nothing but the band of colors termed as spectrum. Okay, spectrum has how many colors? Can you guess and tell me? Yes, that is having 7 colors. What are the colors? Violet, indigo, blue, green, yellow, orange and red. These colors are termed as Vibgea. You can see these colors even in the CD. Can you see the band of colors, children, here? Can you see the band of colors? Yes, this band of colors are otherwise known as a spectrum. Clear, children? Okay. Now we are going to see how the spectrum is formed here. When a white light travels into a prism, that prism splits the white light into 7 colors. This is otherwise called as a spectrum. Next comes the dispersion of light. See, what do you mean by dispersion here? When a beam of white light or a composite light is refracted through a transparent media, such as what are the transparent media so far we have seen? Yes, glass, water, air, all these are known as a transparent media. So, whenever a beam of white light or a composite light is refracted through any transparent media, then it splits into the component colors. So, that is what we have seen spectrum, isn't it? That's what. So, this phenomenon is called the dispersion of light. See here how nicely it is dispersed in the atmosphere. The white color of the sun's ray has dispersed. How nice it is, no, children? So, you would have come across this in your life. Yes. Now, the other topic we are focusing on is the scattering of light. What is scattering? It is the phenomenon in which a beam of light is redirected in all direction when it is interacts with the particle of the medium. See here, children, this is the incident light. Okay, it is the particle. So, when the light falls on the particle, what happens? All the rays interact with the particle, therefore it gets deviated in all directions. Clear, children? So, this deviation, this known as a scattering of light. Clear? So, therefore, the incident ray falls on any particle and it interacts with the particle of the medium, it gets deviated, that is known as a scattering of light. Okay. See the scattering of light, how it takes place in the atmosphere. Clear? So, when a sunlight enters the Earth's atmosphere, the atoms and the molecules of different gases, can you see here? The sun's rays enters into the atmosphere, the atoms and the molecules of different gas present in the atmosphere refract the light. Can you see how it gets refracted? In all possible direction. This is known as the scattering of light. Is the picture clearly explains you, children? Yes. The next one is, see here, the same sun, and here you have so many particles. Can you see what is the molecule here? Can you name the molecule? Very good. It's the water molecules. Water molecules present in the atmosphere only scatters the light. So, this interacting particle is known as the scatterer. Clear, children? This water molecule present in the atmosphere is known as the scatterer. Clear? And why is the sky blue? Here the scattering of blue light by gas molecule in the atmosphere. We will see it little bit later. Clear? Next one. See here what happens. The types of scattering of light. See here, when a beam of light interacts with the constant particle of the medium, it undergoes many kinds of scattering. Depending upon the initial and final energy of the light, we can classify into elastic scattering and inelastic scattering. Clear, children? Let's see what is elastic scattering of the light. When the energy of the incident beam of light and the scattered beam of light are the same, then it is called the elastic scattering. You can easily see here the energy of the incident beam and the scattered beam, everything is same. You have the same amount of energy even in the scattered beam. Then it is known as the elastic scattering. Clear, children? And the next one is the inelastic scattering. Inelastic scattering just opposite to the elastic scattering. If the energy of the incident beam of light and the scattered beam of light are not the same, then it is called the inelastic scattering. So see here, children, you will have along with the incident energy, you have some more energy. Just extra energy is being come out. Therefore, that is known as the inelastic scattering of light. So here, depending upon the nature and size of the scatterer, we can have many types of scattering. First one is the Tindal scattering, second Rayleigh scattering, third Mee scattering and Raman scattering. First we will focus on the Tindal scattering. To explain the Tindal scattering, let me show you one small experiment. Can you see the path of light here, children? Can you see a path of light here? No? You can't see? Yes, you can't see the path of light. Now, what I am going to do is, I am going to put little Dettol, add little Dettol to it. See here, little Dettol I am going to add. When I add a Dettol to it, what happens to it is, it will become a colloidal solution. Okay, that means the particles of the Dettol were hanging in this solution. Now, can you see the path of the light? Tell me. Can you see the path of the light? Can you see the path of the light? Yes. So, what happens here? Let me explain. Okay. Scattering of light rays by the colloidal particles in the colloidal solution is known as the Tindal scattering or Tindal effect. Here what happens, when I put the Dettol into the water, those particles hanging in the water, isn't it, those started scattering the light. So that is known as the Tindal scattering, especially with the colloidal particles. It is known as the Tindal effect. This you would have come across in your life. That is, the dust particles present in the atmosphere. See here, dust particles in the woods, they are scattering the light. So we can see the path of the light very nicely. And also see this, whenever any light enters through the window, the dust particles present in the room scatters the sun's rays. So we can see the path of the rays. Isn't it just so nice pictures, isn't it? Yes, this gives us a clear idea of the Tindal effect. So the Tindal scattering is nothing but when a beam of sunlight enters into the dusty room through a window, then its path becomes visible to us. This is because the tiny dust particles present in the air of the room scatters the beam of light. This is the best example for Tindal scattering. Clear children? Okay. The next one is we are going to focus on Rayleigh scattering. See the Rayleigh scattering, the scattering of the sunlight by the atoms or the molecules of the gas in the Earth's atmosphere is known as the Rayleigh scattering. See here children, the small atoms and molecules present in the Earth's atmosphere scatters the sunlight. This is known as the Rayleigh scattering. Rayleigh scattering law, according to Rayleigh scattering, he states that the amount of scattering of the light is inversely proportional to the fourth power of its wavelength. That is, the amount of scattering is inversely proportional to fourth power of wavelength. That means what? According to him, shorter the wavelength, yes, the greater the scattering. See here, shorter wavelength colors are scattered much more than the longer wavelength colors. Clear children? Okay. See here, from this we can easily explain why the blue color of the sky. Why the sky is blue in color. See what happens here when a sunlight passes through the atmosphere. Blue color is having a very shorter wavelength compared to other colors. So, it is scattered to the greater extent than that of the red color. Therefore, this scattering causes the sky to appear blue. See this picture, it is very clear for you all. See, from sun we get both blue color and red color. What happens? Blue having a shorter wavelength, it gets scattered by the atoms and molecules or air molecules present in the atmosphere. But see the red having a greater wavelength, it just reaches, doesn't get scattered, just reaches the earth, but only the blue scatters away. Therefore, when it gets scattered in all direction and it reaches our eye, only we can see the sky blue in color. Clear children? This picture gives you the clear idea why the sky looks blue. Yes. At the time of sunrise and sunset, the same sky looking red in color. Why it so happen? The light rays from the sun have to travel long distances. Consider this is east and this is west. Here the sun rises, here the sun sets, but the sun is at this corner. It has to travel long distance, as well as at the time of sunset the rays have to travel a long distance. The distance it has to travel long distance. So by the time it could travel, all the blue rays scatters away. So what rays will reach us? Just before we have seen, isn't it? Red light reaches us. Hence, most of the blue lights are scattered away and only the red light which gets least scattered, yes, that reaches us. Therefore, the color of the sun is red at the time of sunrise and sunset. Clear children? So, this is at the noon, midday. What happens? So, children, see at the noon, all the rays reaches the earth directly. So, you can see only the white color of the sun's rays. Next one is the me scattering. See, this me scattering, it takes place when the diameter of the scatterer, we have seen the scatterer particle. Do you remember one scatterer particle I told you? Yes, that is a water particles like that. Okay, the diameter of the scatterer is similar or larger than the wavelength of the incident light, then it takes place. Clear children? Therefore, it is also known as the elastic scattering, and one important point is the amount of scattering is independent of the wavelength. So far we have seen the Rayleigh scattering. There it depends upon the wavelength. Here it is independent of the wavelength. Clear children? So, the white colors of the cloud is how it happens. Here the me scattering is responsible for the white appearance of the cloud. Here when a white light falls on the water drop, all the colors are equally scattered, which together forms the white light. Can see to this, children, see here, the sun's rays, when it falls on the water molecules in the atmosphere, all scatters equally in all direction. Therefore, when it reaches, all the rays reaches us. Therefore, we can see only the white color of the sun's light. See the comparison study of Rayleigh scattering and Mean scattering. Rayleigh scattering purely depends on the wavelength, but Mean scattering depends on the size of the scatter. Can you see the red particles here? Yes, as the size of the particle increases, you can see how it's getting scattered. Next one is the Raman scattering. Okay, when a parallel beam of monochromatic light, do you remember what is monochromatic light? Yes, the light source which emits a single color of light. Okay, when it passes through a gas or a liquid or any transparent solid, only a part of the light rays are scattered. So, the scattered light contains some additional frequencies other than that of the incident frequency, and this type of scattering is known as a Raman scattering, or otherwise known as a Raman effect. See here, children, here these are the incident ray. I have told you it's a monochromatic source of light, so same colors enters into it. When it comes out of the particle after scattering, you can see the incident ray along with the other rays. Can you see the yellow color and the orange color? Yes, the rays of frequency with the incident rays, okay, that is the frequency equal to the incident ray, that is known as the Rayleigh's line, and the rays which are coming out with the frequency other than the frequency of the incident rays, those are known as the Raman line. If the frequency of the scattered rays are lesser than the frequency of the incident ray, then they are known as the Stokes lines, and the rays, those are having the frequency greater than the frequency of the incident ray, those are known as the anti-Stokes lines. It's clear for you all, children? Yes, this picture gives you the clear idea of Raman scattering, Rayleigh line and the Raman line. Okay, therefore, let's see the next one, that is the spectral lines having the frequency equal to the incident ray frequency is known as the Rayleigh line, and the spectral lines which are having the frequencies other than the incident frequency, that is known as the Raman lines. Clear? The lines having the frequencies lower than the incident frequency, that is called the Stokes lines, and the lines having the frequency higher than the incident frequency, those are known as the anti-Stokes lines. Clear for you all, children? Yes. Now we have come to the end of the class. What all the things we have seen? Tell me. Refraction, dispersion and scattering. Based on this, I am going to ask you 3 questions. Question number 1 is, name 3 phenomena of the light involved in the formation of rainbow in the sky. Second question is, why does the bottom of the swimming pool always appear shallower than it really is? Why does the outer space appears black? Answer these questions, post it in my comment box. I'll discuss these answers in my next session. Till then, have a good day. Bye.